You can also think right of 0 is positive. Okay. So basically, if I'm to the left, I'm negative, right? And you could think about that. It doesn't, on the left side of our number line is our negative x's. On the right side is our positive x's. That has no relation to it here, but if it's a way to help you keep it in your mind straight, from the left is negative, from the right is positive, then that is one way to help you keep in mind which is positive and which ones get the minus and which ones get the plus. Okay. So, and you can see in this example here, we're getting it from the plus, right? And that's because we have this sequence here that is, we have this 1.1, right? And we're moving closer to the 1 from the right. So we have 1.1 as a value, 1.01, 1.001, and so on. Okay. And so this one is, you would say for this one, let me just move this. So for this one, you would have this here, and you would say that as you approach 1 from the right, and that's why we end up with this X. You read that arrow as X as it approaches 1 here from the right. Okay. Question. Okay. So let's look at some examples, right? So this one we have negative 4.89, negative 4.899, negative 4.89999, and so on, right? And we want to determine the limit and write it using that notation of X approaches A from the left or X approaches A from the right. A is whatever that value is, right? So if we think of this on that number line, like what we were looking at on the previous slide, right? We can see that our numbers are getting smaller, right? So they're getting smaller as we go along. So that means that we have a larger number and we're getting smaller as we go along. So our first number here would be the negative 4.89. Since it's getting smaller, we would then have over here, maybe this one would be negative 4.899, and this one here would be negative 4.8999, and keeps going until we get here where we're approaching this whole number, because as we keep adding a 9 out there to the end, eventually we're going to get really, really, really close to negative 4.9, right? We're never actually going to catch it, but that's what we are approaching, okay? And so if we wanted to write this in our notation, we would say that we're approaching negative 4.9 from the right. So that's in words, right? So we are approaching negative 4.9 from the right. Okay. And so that means that X is approaching negative 4.9 from the right. So since it's from the right, it is positive. Okay, question. Okay, another example, problem number 12. This is off of page 112. says as x approaches blank, the value of x minus 2 approaches 5. Okay, so for this problem, we have to think about this as, so we want to think of this as x minus 2 equals 5. Okay, so when I add 2 to both sides, I get that x is equal to 7. Okay, so this would say as x approaches 7, the value of x minus 2 approaches 5. Okay, question.
Miss Sandra, before you move on, would you mind scrolling back up to the first example
This one or the previous page?
for number 4 right here? Thank you.
Okay. Yeah, sure. Did you have any questions on it, or you're just capturing stuff?
I'm capturing it. I would like for you to go over that just one more time,
Sure.
if that's okay.
Yeah,
Thank
absolutely. So, the first thing when we get one of these kind of problems, it's important to look, are my numbers increasing or are they decreasing, right? So negative 4.89 is larger than negative 4.899, right? And since that is the case, that means larger numbers go on the right and smaller numbers go on the left. So I used that bit of information to kind of place it out here on a number line. Okay. And these are not symmetrical or anything like that. You could have literally placed them all right here. It's really just to help us like visually understand that we're moving from here in towards the left. Does that make sense?
Yes, that does. Thank you.
Uh-huh. And so basically we want to say, okay, this here is at 2 digits, right? This here has a lot more than 2 digits. So if I rounded this value here to 2 digits, what is that? That's negative. So take my largest number I have that I've been provided and round it to 2 digits. That's negative 4.9, right? Negative 4.9 is smaller than negative 4.89, right? So we're able to place that right here as my far left boundary. So my numbers, I can continue getting closer and closer and closer to this negative 4.9, but I'm never actually going to reach 4.9 because I'm just tacking on extra nines along the way. And so I never actually round it to the 4.9. Okay. And because I'm coming at it from the right, I'm coming from the right, right? From the right. That's why I get that plus sign. If I was coming at it from the left, I would have had a minus sign up there.
And if you were coming from the left, would that turn into a positive, the 4.9, or it would still be a negative?
So it could be negative, right? Like our example, oh, these are both positives. But so let me just make one up. So if we were coming here, and this is say negative 2.1, and maybe this is negative, or yeah, negative 2.09, and this could be negative 2.099, and you keep adding all those zeros, eventually it will round up to 2.1, right? If you were to look at this value here, this is negative 2.9, 2.09 will always be smaller than this one, right? And so since we're approaching it from this way, you could still be negative, right? But for this one, we are approaching negative 2.1 from the left, right? So we would say that x approaches negative 2.1 from the left.
Thank you for that.
Uh-huh. Okay. Questions? All right. So one more example where it says the notation and how do we, and really we're saying, how do we read this, right? And so that is read, you would say this is read as the limit as x approaches 5. So it has a minus. So is that from the left or the right?
Left.
The left. From the left, right? Of this function f of x. Okay, that's how you would read what's there in that circle. The limit as x approaches 5 from the left of f of x. Okay. Question. Okay, so I see a note in my chat about going back to a previous page. What you can do is at the end of class, all of these notes will be uploaded into Canvas and you can fill in any holes that you might have at that point, okay? All right, so let's look at some other examples, right? I told you we were gonna look at these. Oh, actually, I skipped and we got to talk about this theorem. All right, so here we have this theorem that says that as x approaches some value a, right, then the limit of the function is this capital L, which is, you know, for limit, right? If the limit from the left exists and the limit from the right exists, and they are both the same value. That's really what this is saying, okay? So ultimately, what it's saying is, one, if I have a limit as x approaches some value, we'll use a from the left of some function equals this capital L value, right? It could be 22, 75, 1/5, whatever that may be, okay? And I have a limit as x approaches that same a, but from the right, same function. And it also equals L. So those both have to equal L, okay? If both of those conditions are met, then, and only then, will the limit as x approaches a, no left or no right. So if there's no plus, no minus up there, that means it's true from the left and the right, both directions for this function, and it equals that value of our f. Okay, so that's really what that theorem is saying, okay? And so if all the values are close to that L for the value of x, then they're sufficiently close, but not equal to that A value. Okay. And so honestly, I'm always going to present you guys, I'm going to show you just a snippet copy out of the textbook of what the theorem is. But then really the goodness of the class and the lecture is being able to see some of those examples and how we interpret that through working through problems is more important than the words of the theorem itself. Okay. Question. All right. So how are we going to implement this in practice? So we're going to do that through a couple of different examples. Okay. So first we want to look at determining limits graphically. That's what these kind of problems are. So problem 34, 36, 38 in our textbook, they're all going to be looking at this graph to help determine what the limit is. Okay. So for this first one, okay, you can see that we don't have a plus or a minus here, but to determine if a limit exists, we have to check from the left, we have to check from the right. If those are equal, then the limit exists. Okay, so let's start with this one. So we want to know our G function, that's all of this here in the red, that's our G graph. What is the limit as x approaches 0? Okay, so we're looking at x equal to 0. So x equals 0 right here, right? So x equal to 0, then our limit, so we have to do, what is our limit as x approaches 0 from the left? And we want to know what if our limit of x approaches 0 from the right for our g function. Okay, so what are those values? So let's say if I'm on this graph, if I'm on the graph from the, I'm going to do two different colors to help you guys visually see this. Okay. So I'm going to do this a different color as well. So our green, our line there in the middle is, so the purple line is what we're approaching, right? Purple is because this tells me that x is approaching 0. So the one thing I will tell you guys is I like to try and use a lot of colors to help draw your eyes to understanding and visually seeing what's going on. Okay, so if I ever use a color that you're not seeing very well, because it's, you know, if you have color blindness or color sensitive, please just don't hesitate to say, I can't really see that color. Can you pick another one? Okay. Jasmine, I see you're unmuted. Do you have a question? Okay. Just wanting to make sure. Okay, so as we're approaching from the left, that means here's my left, right? And if I'm approaching from the left, that means I'm going this way. So I want to know as my x value gets close to 0, from this direction, I am at what is my y value there, right? So that's really what this is saying. So as I approach from the left, my y value is 3. Do you guys see that? This here is my y value. Okay. Now, when I approach from the right, you can see I'm on this graph here as well. I like to say, go to the graph, write it down. It also is at 3. Okay. My y value. So we could have said for this one, we could have wrote the graph up to 3 and saw that as well. Okay, so that's from the right, left, and this one is from the right.
Professor,
okay? Yes.
question. How did you get to the 3 though? Like what I mean, we couldn't use any of the numbers. And how did 3 make the determination?
Sure. Yeah, because it's where does my graph cross x equals 0, right? Because I want to know what is my y value when x is equal to 0. So if I erase this stuff out of here, if I'm coming from the left, right? If I just get on the graph and I'm coming from the left, I hit that 0, that purple line at y equals 3, right?
Okay, so it's where the x crosses the y. That's where we get the answer from the left and the right.
Yeah.
Okay, thank you.
And for the green, you notice I have a graph here, right? And I have a graph here, but this graph doesn't ever get me close to 0. So I kind of have to ignore this piece. This one does. So I write it and I get to 3. And we'll look at an example here in a minute, the one, right? Where I have to look at both graphs. Okay. All right, so I can see here then that the limit as x approaches 0 from both the left and the right, so I don't put any value there of my function, is equal to 3 because both of those equaled 3. Okay, makes sense? All
Sorry,
right.
can you repeat that again?
Yep, because my limit from the left and my limit from the right are equal to each other, then the overall limit is equal to that. So that goes back to this right here. If my limit from the left is 3 and my limit from the right is 3, then my limit is 3. Make sense? Okay, so let's look at this next one. This next one is asking just for x as it approaches from 1. So now here's x equal to 1, right? And I want to know as it approaches from the right. So I'm going to get on my thing here, write it around, and I'm here at this point. So my y value here is -1. So my limit as x approaches 1 from the right of my g of x function, I need to make sure that's up online with the limit and not that. This is like a sub part of the word limit. Okay, is equal to -1. Okay. Now, question 38 is asking for 1, not 1 from the right or 1 from the left. So we actually have to look at the limit as x approaches 1 from the left of our function, right? So I want to get to this 1. So I'm coming here, and as I approach 1 from the left, that's this point over here. So we come up, we're on this graph, and it's this point here, y equals to 4. Okay. So now I already know, because I did it from the right already in the previous problem. So my limit as x approaches 1 from the right, we got was equal to -1, right? So we know these are different, right? So as my inputs approach 1 from the left, my outputs or my y approaches that value 4. Thus, the limit from the left is 4. In the red, as my inputs approach 1 from the right, my outputs approach -1, and thus the limit from the right is -1. And so since the limit from the left is 4, it's not the same as the limit from the right, which was -1. We would say that the limit as x approaches 1 for my g of x does not exist. And you can write that as dne. Okay? So there's an example of how we have from the left to the right, they're the same, so the overall limit exists. And then here's an example where they are approaching 2 different values, right? Because this one is approaching this value up here, and this one's approaching a value down here. They're not the same. Therefore, that limit itself does not exist. Okay? Question.
What is the g of x on the graph?
Say that one more time.
What is the g of x on the graph?
The I'm sorry, I'm not understanding the word you're saying.
What I said, what is the g of x on the graph? The location of the g of x on the graph.
So for which one?
Or in another word, what the meaning of g of x?
I'm not sure what you're meaning by g of x.
I think he's asking what is g of x representing? That's what he's asking, I think.
Yes.
X. Sorry. I have an ear infection right now, so I can only hear out of one ear, so I really do apologize. And the other ear is ringing, so I do apologize.
That's fine.
The g of x on the graph, so everything, all of the red that this showed us, all of the red, that is g of x. All of this dot and this, that's all g of x. Is that what you are asking?
Yes, thank you.
Uh-huh. Okay. Any other questions?
So we only consider the hollow circles. We don't consider the filled in circle.
So in this case, we are considering the hollows because that's what the graph leads us to, right? Because this is just one specific point, whereas this is the graph coming from the right or the left. This is just equal to 1.
Okay, got it. Thank you.
Uh-huh. And put the markings back on here. All right. Okay. So there will be times when you need to graph a function and then determine the specific limits, okay? So problems like 61 through 78 on page 113 in your textbook will be of that nature. So for this first one, number 62, we're just given a function. We're given f of x squared, and then asked to determine the limit of x approaching -1 and the limit as x approaches 0. Okay, so first we have to graph that. So I would say, like, if I put 0 in here, that's 0 times 0, 0 squared is 0. 1 squared is 1. 2 squared is 4, right? The same is true on the left if I do the negatives. So this graph looks something like this. Okay? So now that we have that, now we can visually look at this limit here as well. So the first one, if we want to find the limit of our function, right, as x approaches -1, okay? So we have to look at that from the left and the right. So -1 from the left, and we want to look at the limit as x approaches -1 from the right for our same function, right? So what are those? Let's do a couple of colors to help us visually see that. Okay, so let's go, where is x equal to -1? That's the first thing. So here is x equal to -1, right? So I'm going to just draw that line in there to kind of help us visually see that. So for the red, if we're coming from the left, I'm coming from the left, and I am approaching this value here, my y value is also +1. Okay, so as I approach x equal to -1 from the left, my y is approaching +1. Okay. Similarly, if I'm approaching from the right, I get up to here, I followed my graph around, and you will see as I approach x equal to -1 from the right side, my x value is also 1. Okay, so again, because those values are the same, I could say that the limit as x approaches -1 from the left and the right, both of my function is equal to 1. Okay, so I'm going to give you guys about, I'll just give you about a minute to think about this one. So what if I wanted to know the limit as of my function as x approaches 0 from the left and the limit as x approaches 0 from the right?
Professor, question.
Yes.
So when we approach from the left, we look at the y-axis. When we approach from the right, we look at the x-axis.
Nope, you always look at this tells me what x I'm doing. So that's where we would come in here and draw our line. So we're looking at the line. I'm going to change that color. I don't like that. We're going to do the line x equals 0. So what is my y value? Where does my graph cross or meet that line when I'm coming from the left, and where does it intersect when I'm coming from the right?
At 0?
At 0 for both of them, right? Because here you can see I'm coming around. That occurs at 0. Where x is equal to 0, my y is equal to 0, right? And then for this one, as I'm coming around here, again, as x equals 0, y equals 0. So I would say again, then here, that is bad color, that my limit as x approaches 0 in general of this function is going to equal 0. Okay, question? All right, so here's one where we have to graph, but it's not as easy as the polynomial that we just graphed, right? So since x minus 2, if x is equal, so first of all, we have to look at this and put in any asymptotes, right? Because we cannot, so asymptote, where it's actually, I'm going to define it as a vertical asymptote. When the denominator equals 0. Okay, so our denominator here is x plus 2. So it cannot equal 0, right? So I minus 2 from both sides. So x cannot equal negative 2. All right, that's going to make my problem undefined. So I come over here to negative 2. I can put in an asymptote. That means my graph cannot intersect that line. I can approach it. I can get really close to it. I just can't cross it. Okay. So we have to exclude that from the graph of our domain. Okay. So other than that, I would say for this kind of problem, it might just be easiest to build ourselves a table of x and y values. Okay. I would say we need to get a couple on this side of our asymptote, a couple of points on this side of our asymptote, and we'll be good. So I'm going to just do negative 3, negative 3. I'm going to do negative 2.5 because I'm getting closer to 2. Negative 2.1, right? So I'm getting really close to this 2, but I can't actually equal it or it'll be undefined. And then, so that kind of gives me on the left side of the asymptote 3 points. And now let's do a couple of points on the other side as well. So if I do negative, so I want to do like 3 or 4 points on this side. So negative 1.9, negative 1.5, negative 1. Okay. And I do 0 if I wanted. That one would be a much easier one to see. So I plug in negative 3 into our equation over here. Negative, or 4 times negative 3 plus 9 divided by negative 3 plus 2. So that's going to give me a value of positive 3. If I can continue putting all these, if I put negative 2.5 into the equation, I'm going to get, this is positive 2. This will be negative 6. This will be positive 14. And all I did was the algebra of it here. Nothing super shocking. This would be, if I had zeros here, that's going to give me 9 halves. So we could put that in here too. Okay. So now I just need to plot those points. So I have negative 3, 3. So here's negative 3, 3. I have negative 2.52, so I'm halfway here and it's at 2. And then I have this point, negative 2.1 and negative 6. So here's negative 1, 2, 3, 4, 5, negative 6, and we're much closer to that line over here. Okay, so we can kind of see that the shape is something like this. Okay, that's just the first half. Okay, the second half, I'm not going to graph this one because I didn't leave enough room to go 14 high. But we can graph negative 1.5. So here's 1.5, and that's up at positive 6. So 1, 2, 3, 4, 5. Here's 1.5 positive 6. Here's negative 1 and 5. And here is 0 and 4.5. Okay. So you can see this one would shoot way up here. Because we know at negative 1.9, it goes all the way up there to 14, right? So this actually, we've graphed it. We can kind of see now what it is, the shape of it. And so then we can Now look at our limits from this. Okay. So this problem asked us to find a couple. It asked us, first, we're going to look at finding the limit as x approaches infinity. Okay, so this is infinity out here, right? So this would be as x approaches infinity, because this right here is 1, 2, 3, 4, 5, all the way out here to infinity. And you can see this graph will just go on and on to infinity as well. Okay. So as our input x gets larger and larger, our output gets closer and closer to this line right here. And that line is at 1, 2, 3, y equal to 4. So we can see here, when we're looking at the limit as x approaches infinity, then our y value gets really close to 4. Okay. Similarly, when we're looking at our, actually, let's make that blue. When we're looking at, now we want to look at as x gets closer to -2, that's that asymptote, right? We need to look at it from the left and from the right. So let's look at it from the left first. So as I get closer to -2 from the left, you can see my y value is going to go all the way to -infinity, right? Because I'm going to just keep, as I get closer and closer and closer to that line, my y value is going to be unbounded to the -infinity. So that's not ever going to stop. It's just going to keep going on forever. Okay. But let's do orange. So now what if I want to look at it from the right with the plus sign, right? So now I'm coming in here, getting really close, and I'm bounded. I'm going all the way up to positive infinity. Okay. And because these two are not the same, my limit as x approaches -2 does not exist. Okay, and that's since the function value for as x approaches -2 from the left decreases without bound, and the function value as it approaches -2 from the right increases without bound to the positive, then that limit does not exist, because we have one's going to -infinity and the other's going to positive infinity, and therefore that limit does not exist. Question?
I have here you go.
Oh, you can go ahead.
I just want to know how you got like the Y numbers.
So you just I just picked random x's, 3 on the left side of the asymptote, and I didn't graph this one, so I picked 3 on the right side of the asymptote to give us the graphical picture. So I take this -3. So here's my function. So g of x is 4 times 3 plus 9 divided by 3 plus 2. That simplifies to +3.
Oh, okay, I gotcha.
And I just kind of did that ahead of class in my notes for all of those, because I know you guys all can do the algebra of that, and so that's not really the lesson. The lesson is how we graph it and then find the limit based off of it. Okay. Questions? Anna, did you also have a question?
Yes, it was the same thing.
Okay, perfect.
Yeah, thank you.
Yeah, of course. Any other questions before we move on? All right, so this is the last example of this section, then we'll take a 10-minute break and then come back and finish the other two sections. So this one is a piecewise function, so we have to graph both of these functions and then determine it. So I'm going to first graph the x squared, okay? So x squared, we graphed that a little earlier. That was 1, 2, so this would be 2, 3, 4. It mirrors in the negatives. Okay, so that is x squared. Okay, now this problem says we use that for x is less than -1. Okay, so let's make that purple. But we want to do this only for x less than -1. So what we have to do here, I'm going to make this a little different how I do it. There you go. Mostly because I want that, I should have took that dot out first. All right. So it's at -1. I'm going to put a hollow dot here because it would look something like that. And the reason I put the hollow dot there is because this problem does not have equality with it. Okay. So what that's saying is we have to ignore all of this because that is not part of the purple graph. The purple graph is really just this piece of the graph right here and all the way up. Okay. All right. So that's our purple graph. And I put that hollow dot to tell me that it gets really close to -1, but it can't include -1 because I don't have equality. If I had an equal sign here, then that would be a solid dot, but I don't, so it's a hollow dot. Okay. Now let's pick this next graph. We'll make it blue. This is just x plus 2. So we come up here, and if x is 0, then y is +2. If x is -1, then y is +1. So that's here. Again, it's hollow because there's no equality. So ultimately, we have this line is what that would look like if it was an equality, right? But we're not going to count this portion of that line because it is less than the 1. And so we're really only looking at this piece right here. Okay, so now that we have that graph, we can do what we need to discuss about our limits. Because really, ultimately, we're looking to determine what is the limit as x approaches this negative. Okay, so think of that. This is our x equal to -1. This is that we want to see how it's approaching from the left, and we want to see how it's approaching from the right. Okay, so as I approach from the left, right, you can see that my limit as x approaches -1 from the left of this function, and this function is the piecewise, so it's both functions together, that's equal to +1. Okay. Also, that's probably too close in color. As I approach from the right, so my limit as x approaches -1 from the right of this function is also y equals to 1. No, I don't want purple. So what I have then here is that my limit as x approaches -1 of this function g of x is going to equal 1 because these two values are the same. Okay, question. All right, so any questions before we take a break?
Quick question, Professor.
Sure.
Why is it 1 and not -1?
Because it's our y value. Our x value is -1, so here's -1, but our y value is +1.
Okay, got it.
Uh-huh.
Thank you.
You're welcome. Any other questions? All right, so let's take a 10-minute break. It is 8:28. Let's come back at 8:40. Okay, so we'll come back at 8:40 p.m. and cover the next two sections. They shouldn't take as long just because they're not as we kind of had to establish some thought process here. So we'll come back at 8:40 and then we will continue. Okay. All right, it is 8:40, so let's go ahead and continue on to section 2. Section 2 starts on page 116 in your textbook. So in this section, we're going to develop and use the limit properties to calculate limits. We're also going to determine whether a function is continuous at a given point. Okay, so what you're seeing here is you can go to your textbook, page 116 and 117, to get these limit properties, but I've also put them out here in our notes so you have them in one nice, neat area. Okay, and so we're not going to cover each and every one of them specifically down this list, but we will look at them as we are working through problems. And I'll say, hey, this is from L1, which is the limit of a constant. And so basically the limit of a constant is that constant, and so on. Okay, and then we'll see how those work out in practice. Okay. Then we have a couple of definitions and theorems here. So the first theorem really is, it says that this is really the theorem of limits of rational numbers. And so it just says that for any rational function that we have as x approaches a for that, then the value of that is going to be that function evaluated at a is the limit. Okay, and we'll see some of that in example as well. And then there's some definitions here. What does it mean to be continuous? It means that the function, you can evaluate the function at a. It means that the limit exists and that the limit is the same as the output. Okay. And so we can have something can be continuous over an open interval. But also there's times when you saw that we had those, circles on the graph. So that would be points where the graph is discontinuous. And when you have when a graph is discontinuous, that leaves the potential of the limit not. Okay. All right. So now let's go ahead and get into some of the examples. So what we have here first is on page 124. If I wanted to determine, it gives me here that the limit as x approaches 3 of 7 is 3. Is this true or false? That's what this problem is. And this here, that is false, right? Because by L1, that's that limit property or limit principle number 1, that tells me that if I had the limit as x approaches any value of a constant, it is equal to the constant itself. Okay, so this here saying that the limit as x approaches 3 of 7 is equal to 3, that's false because it would have to equal itself. Okay. So this next one says if we have g is discontinuous at x equal to 3, then g of 3 must not exist. Okay, true or false? This here is also false. It's a false statement. And we can do that by a counterexample, right? And so it's false. And we could say that just because there is a jump in the graph, like we saw earlier, jump in the graph we'll say for this one at x equals 3, it doesn't mean that g of 3 doesn't exist. So I could give you a counter example, right? So if this is 1, 2, 3. So let's just say we have some graph that looks like this. So if it jumps, it has that hollow point, it's discontinuous. If that's all there is to the graph, then sure, it doesn't exist. But remember, what if we have another point, something like this, and you could see that there is a value for g of x, it just isn't on that particular line. So there is a jump, but that part that the point lies outside of that line. So this is just a counterexample to show that, hey, I could be discontinuous at x, but I could also still have a value of g of x, right? So my function can be evaluated at that point. It just isn't part of the graph or the line, okay? Questions? So now let's use our theorem number 2 to answer some of these. So that's the limits of our rational function, right? And so for the limit as x approaches 2 of this 4x minus 5, really what that's telling me, what that theorem tells me, theorem 2, right? Theorem 2 is what we're looking at here. That is going to give me then 4 times 2 minus 5, right? All I'm doing is substituting in this for all of the a's or all the x's. And so this is going to give me a value of 8 minus 5, which is 3. So the limit of as x approaches 2 of this 4x minus 5 is equal to 3. Very similar, we can plug this 5 into all of the x's for here. And that's going to give me 5 squared minus 6 times 5 plus 9. So that's 25 minus 30 plus 9 is equal to 4. Questions?
So
Okay.
for number 10 and number 14, you're just basically solving for the equation more than like a true or false type answer.
Yes, that is correct. So this is the instructions, like if you, this is on page, I didn't write the page number down here, but it is on page 124 of your textbook. And the instructions tell you to use the theorem, theorem number 2, to find each limit. And so theorem number 2 right here was basically just telling us that we plug this into here and get out the answer. Okay. So now we have one more problem here. So we could plug the 3 into here and into here. So that's going to give me 3 squared minus 25 over 3 squared minus 5. And so this is negative 16 over 4, which reduces to negative 4. Okay, question. So carrying on, we have 3 goes into here, 3 goes into here. So that gives me 3 squared minus 9 divided by 3 minus 3. That gives me 0 over 0. Okay. If it was some number divided by 0, that's undefined. It does not exist. But when I get this 0 over 0, this is an indeterminate form. Okay. So it's the indeterminate form. And so in order to find the limit, we first have to simplify that equation before we do that, okay? So I want to point out that as a little refresher from algebra days, if I have a squared minus b squared, that's a perfect square minus a perfect square, that factors as a minus b, a plus b, okay? So what we have over here, we have this x squared minus 3 squared, right? So if a equals x and b equals 3, then that's going to factor as x minus 3, x plus 3, okay? So I'm going to put these in green. So I factor this, I have my limit as x approaches 3, and I factor this. So that gives me x minus 3, x plus 3 over x minus 3, okay? So now you can see I have an x minus 3 in the numerator and an x minus 3 in the denominator. So that then simplifies to the limit as x approaches 3 is equal to just x plus 3. Okay, so now that is 3 plus 3, which is 6. So I actually do have a limit here because once I get done with that indeterminate form, or I basically, when I have a factor in the numerator and the denominator, I don't actually end up with a vertical asymptote, right? What I end up with is a hole in the graph at that specific point. So if you guys remember back to algebra days, when you have a graph where you have a factor in the numerator and the denominator, everywhere that equals 0, I'm going to have a hole in the graph. Okay, so I'll have a hole in the graph at x equal to 3, but I won't have, the graph won't have to come to a screeching halt because of the denominator cannot equal positive 3. Okay, question.
So would the answer be 0 or would it be 6?
6. Yeah. This next example, we'll see another form of the indeterminate form, right? So we plug in that 2. I'm going to do just the different colors to break it up. So we have 2 squared plus 3 times 2 minus 10 divided by 2 squared minus 4 times 2 plus 4. Those are going to be 0 over 0. Okay, so again, we have that indeterminate form, so we have to factor. So we'll say our limit as x approaches 2. We're going to factor this, so that would be x plus 5, x minus 2, divided by factoring the denominator, that's x minus 2, x minus 2. Okay, you can see that we have an x minus 2 in the numerator and in the denominator, so those will cancel out with each other. And that leaves us with the limit as x approaches 2 of this x plus 5 over x minus 2. So we can simplify that. So that's going to give me 2 plus 5 over 2 minus 2. So that is 7 over 0. You can see here now that that is undefined, right? Since that is undefined and we can't simplify that term anymore, we would say that the limit does not exist. Questions? All right, so for this next problem, this is on page 116, 117, number 31 through 46. We're asked to use our limit properties, right? So before we were looking at theorem 2, now we want to use our limit properties. Okay, so for these problems, we want to use our limit property. So first, we will divide all of our terms by the highest power in the denominator. Okay, so divide by highest, so divide all terms by highest power in the denominator. Okay, so the highest power in the denominator is x to the 1 in this case. Okay, so we have to divide all terms by x. Okay, so we have our limit as x approaches infinity of 7x divided by x plus 5 divided by x over 3x divided by x. So that's what it means when we're dividing all terms in the denominator by the highest power, okay? And we're going to use the fact that we have the limit as x approaches infinity of 1 over x is equal to 0. Think about that, right? If I had 1 over 1, that equals 1, right? If x equals 1. If x equals 100, that's 1 over 100. So that is 0.01. Okay? 1 over 10,000, right? Did I put 10,000? 1 over 100,000 is 0.1234, all those zeros, right? So as as my x value gets larger and larger, my value here gets closer and closer to 0, right? So as my x gets bigger and bigger and bigger, my y gets closer and closer to 0. Okay? So that's just what you can think of as a fact. Okay? So now that we know that information, well, first of all, I can see these x's will cancel with each other and these will cancel with each other. So just as I have 1 over 100,000 gets really closer to 0, if I had a 5 here, I'm still going to get really close to 0. So I can say this here is going to go to 0. If I get a number infinitely large, that's really large, I'm going to get really close to 0. Okay? So this tells me then that I have the limit as x approaches infinity, right? And that gives me 7 plus this 5 over x over 3. And again, that goes to 0, right? So when I plug infinity into there, and so that is then going to give me a value of 7 over 3, right? So the limit of this problem as x approaches infinity, I'm going to get, as x gets infinitely closer to infinity, my y value is going to be much closer to 7 over 3. Okay, questions? Okay, so we have lots of examples. I like to do a lot of examples so that you guys see a wide range of examples. And so when you come to your homework, it's not as, you've kind of been exposed to a lot of different things, okay? So this is just a couple of more examples here before we switch over to our third and final section for the evening. All right, so let me make sure, yeah, that was number 32. Yeah, number 40. All right, so for this one, first we want to divide all our terms by the highest power, right? So again, divide terms by highest power. In the denominator, okay? That is, for this problem, that is x cubed, right? This is the highest power. So the x cubed. So we have the limit as x approaches infinity. We have x to the 5 over x cubed. We have x cubed over x cubed plus 4x over x cubed plus 10 over x cubed. Okay, so long as we do it to all of the terms, that's fine, and we're not changing the dynamics of the problem. Okay, so for this one, very similar to the part I showed you all ago, we have the fact that the limit as x approaches infinity of 1 over x to some value, that's also equal to 0. That just means we're getting there faster, right? If I had 1 over 1 squared, we'll just say it's even squared, that's still 1. I have 1 over 10 squared, that's 1 over 100, that's 0.01, right? And we can continue, and you can see that this is going to ultimately, the larger my x value, the closer I get to 0, okay? So same thought process here, and that's because when this is going to cancel away, this will cancel here and leave us with a 2, this will cancel and leave us with a 2 up here. So that gives us the limit as x approaches infinity of x squared over 1 plus 4 over x squared plus 10 over x cubed. Okay, so when we plug infinity into this problem, right, we end up with, first of all, this is going to drive to 0, right, based on our thing over here that says x raised to some power is going to still drive to 0. So this gives me then that the limit as x approaches infinity is x squared over 1 plus 0 plus 0. And so when I plug in my infinity, I get infinity squared, right? But infinity squared is really just infinity, because if I think I've reached it, there's something else out there. And so infinity squared really is just infinity, okay? And therefore, we don't have a definitive value. I can't say pinpoint an exact value because infinity is so far out there and we can't ever reach it. Therefore, it doesn't exist in the world of a limit, okay? So if you ever come up with a limit that is negative infinity or positive infinity, then that limit does not exist because we can't actually ever get out to it. Because just as we, like I mentioned, as we think that we're getting there, there's something else even further. Okay? Question. All right. So let's look at this one. We're going to use this as, this will use a handful of the different problem limit principles. The first one we'll use is L2. Okay, the first one is L2, and so that's where we're saying when we have the square root of a value, actually this one, we can rewrite it. And so that's really all we're going to do over here is just rewrite that. So we're going to rewrite this as the square root, and we're going to put the limit on the inside, okay, of x squared minus 9, okay? And so this here is by L2, okay? All right, so now we're going to use L3. I don't know how to, I'll write it here, L2. And so now we're going to use L3. L3 here is telling me that if I have two functions added or subtracted from each other, I could split those out to where the limits are in front of each of them individually instead of together, collectively. Okay, so that then is going to allow me to write this as the limit as x approaches 4 of x squared minus the limit as x approaches 4 of 9. Okay, and this is done by the L3. Okay, let me write by L2, and this is by L3. Okay, now what we can do is we're going to use a combination of L2 and L1. Okay, so for this piece of it, okay, that is the limit as x approaches 4 of x, and we're bringing the squared. So we're kind of bringing it on the outside, okay? Minus 9, okay? And that is because, remember, by L1, the constant, so this is, for the first term, it's by L2, and the second one is by L1. So this is by the constant, and this is the one we've already looked at in the first step, okay? So now we've broken it out like this, and we could say, well, the limit here, as x approaches 4, that is just 4, and then we have that squared, and then minus 9, okay? So this gives me the square root of 16 minus 7, 16 minus 9, which gives me the square root of 7. So my limit for this problem is going to be the square root of 7. Now, we could have literally just plugged 4 into here, right? If we would have plugged 4 into here, we would have gotten the square root of 16 minus 9. And we would have, in like one step, received this. But the instructions weren't to do that. The instructions were step through each of those limit properties to get to that solution. Okay? Question. All right. So now the last example here in this section is number 60, and is the function given by f of x equals 3x minus 2 continuous at x equal to 5, y or y not. Okay, so what we first have to do is we need to find the function value when x equals 5. Okay, so when the function evaluated at 5, so that's going to be 3 times 5 minus 2. So that's 15 minus 2, it equals 13. Hence, f of x, so basically, hence f of 5 exists, right? Because we had that whole checklist of things that has to be in, that we have to make sure are true. Okay, so next we want to find the limit as x approaches 5. Okay, so it follows that from the theorem on limits of rational functions that we can find the limit by substitution. Okay, so we're going to find the limit as x approaches 5 of f of x. And that equals 3 times 5 minus 2, which is 13. Okay, therefore we would say that the limit, so therefore I'm out of space down here, so I'm going to just come up here and write. So therefore the limit as x approaches 5 of our function equals 13, which is the same as f of x evaluated, right? And we know that the function is continuous at x equal to 5. Okay, question. All right, so that is all of this section, and we have one more section to cover for this evening. Okay, so for this one in section 3, this begins on page 127 in your textbook. And in this section, we're going to compute an average rate of change. Okay, you could think of rate of change as a ratio of two quantities. And actually, by definition, the average rate of change of y with respect to x, as x changes from x1 to x2, it's the ratio of our output to the change, right? And so this brings us back to our pre-calc 1 days, where we have y2 minus y1 over x2 minus x1, right? That's really just that rate of change. It can also be written as f of x2 minus f of x1 over x2 minus x1, right? So what is my y value? What is the y value, or my function evaluated at my x2 minus my function evaluated at x1? And of course, x2 cannot equal x1, because otherwise it would be 0 and they would be undefined. Okay? So the graphic here to the left, that is what is provided on page 129 of your textbook. So I just put it in here to help you have that visual of our rate of change, right? So in algebra days, we were looking at these rates of change for a straight line. That is here what you see, the blue line, which is that secant line, okay? And eventually, though, throughout this, the course of this class, we're going to learn, we're not going to really measure from point A to point B, but we'll learn how to measure the distance under this curve here, like how much that distance is versus looking at the distance from with the straight line, okay? So but we're kind of slowly building up some tools to be able to do that in future sections. Okay. So any questions on the rate of change? So it's really, think about it in terms of slope, right? All right, so let's look at an example. So we have we want to find the average rate of change. We're given a function and we're given our x1 and x2 values. So we first have to find our y values that correspond to the given x values, right? So I want to find g of 8, that is my x1, right? So I'll write that actually here. G of x1 is g of 8. G of 8 is 5 times 8 minus 4. So that's 40 minus 4, which is 36. I want to find my G of x2. That's G of 11. So 5 times 11 minus 4. So that's 55 minus 4. It's 51. Okay. So the average rate of change will be y2 minus y1 over x2 minus x1. So that is 51 minus 36 over 11 minus 8. So that is 15 over 3, which simplifies to 5. Okay, question. Okay.
Professor, can you go back? Can you just leave it right there for 1 second? Thank you. I got it. Thank you.
Yeah. All right, so this is the same view that I gave you a while ago. We're going to call this, though, the difference quotient. This will become important in the next section that we'll cover next Monday, where we actually find the limit using the different quotient and such. But what does that mean, right? The difference quotient as a rate of change really is just given by f of x plus h minus f of x divided by h, right? Where h cannot equal 0, okay? So all I'm saying is I have my x value here. My second value is x plus some value h, right? So my first point is at x. My second point is at x plus h. So I'm just substituting that in instead. And the difference between these two, right? If I had x minus x plus h, that is really just, or actually I do my x2, right? So x2 minus x1 is really just x plus h minus x, which is h. And so that's what that is in my denominator. And my numerator is just taking my my function evaluated at x plus h, and then my function evaluated at just x. Okay, so it's the same thing. It's the y2 minus y1 over x2 minus x1, but it's just in a different form. Okay. All right, so when we look at it here, if you look on page 134 in your textbook, the instructions for this actually say for each of the functions, they want you to find the simplified form of the difference quotient, and then complete the table. So the first thing we need to do is get the simplified form of the difference quotient. So all right, so the simplified form of the difference quotient, okay? So we substitute x plus h for x. Okay, so what is f of x plus h? So in this case, our function is 4x squared. So we're replacing the x with x plus h. Okay, so that is 4 times x plus h times x plus h, which is 4 times x squared plus 2xh plus h squared, which is, now we distribute the 4, we get 4x squared plus 8xh plus 4h squared. Okay, did everybody see what we were doing there? All I did was plug in x plus h in there and expand it out. Questions? All right, so now then the difference quotient. So the difference quotient then, remember I put on the other page, was f of x plus h minus f of x divided by h, right? So we just substitute that in. I've already calculated all of this. We're going to substitute in for here, and this will substitute in just the original equation, which was 4x squared. Okay, so we substitute all that in and we get 4x squared plus 8xh plus 4h squared minus 4x squared divided by h. Okay, so that's all done by substituting. So we can simplify this. I could see I have this negative 4x squared and a positive 4x squared. So that leaves me with 8xh plus 4h squared over h. I could factor an h out of both terms in the numerator. So that's going to leave me with 8x plus 4h over h. You can see I have an h in the numerator and h in the denominator, so those will cancel. And that leaves me with 8x plus 4h. Okay, so this here is 8x plus 4h. That's what it simplifies down to. That's what we've done. So now that we have that, we can actually plug in. We were given x is equal to 5, and we have these various h values. So what does that look like for our solution? So this first one would be 8 times 5 plus 4 times 2. That equals 48. If we did 8 times 5 plus 4 times 1, that equals 44. This one is 8 times 5 plus 4 times 0.1. That equals 40.4. And this one is 8 times 5 plus 4 times 0.01. And that is 40.04. So you can see the smaller we get for our h value, the closer and closer we get to the value of 40. Okay. Questions? All right. So the last problem I have for you guys tonight, it's an application problem. And so a lot of the problems that we're going to work in this class will deal with profit, revenue, expenses, right? So your total profit is going to equal your revenue minus your expenses. So how much money did I bring in? How much money did I have to pay out? And then what's left is my profit, right? So we're going to do various things with cost, profit, revenue, those sort of things throughout the semester, for example wise. So for this one, we're looking at total revenue. So we have, suppose that Fast Trends determines that the revenue in dollars for the sales of X number of iPod holders is given by R of X equals this formula here, okay? So we want to find R of 300 minus R of 305 minus R of 300 and interpret those results. So basically, we're saying, okay, so what if my X value, or I sold 300 of these iPod holders, right? Or 300. So my X2, so X2 equals 305, X1 equals 300, okay? And R of 305 gives me my Y value for that X2, and R of 300 gives me my Y value of X equal to 300, okay? So when I plug that in, if I plug in R of 305, I'm going to get, that is that negative 0.001 times 305 squared plus 150 times 305. I'm going to just move this here so I could put it all on one line. And that is 45,656.98. Okay. My revenue, if I sold 300, is going to be the negative 0.001 times 300 squared plus 150 times 300. And that's going to give me a value of 44,910. Okay. So now when I do my R of 300 or R of 305 minus my revenue of evaluated at 300 divided by 305 minus 300, that's going to give me it's going to give me the 45,450 or 45,656. I'm going to put 657 minus 44,910. Okay, and divided by 5, and that's going to give me a value of about $149.40. So what does that mean, right? That's what this here is saying, and interpret that for us, right? And so ultimately what that's saying is the average increase in revenue from selling that 305th unit is $149.40. Okay, so interpretation. That's saying that the average increase in revenue from selling the 305th unit is $149.40. Okay? Question. All right. Well, it was a long night, a lot of material because we had that class tour to cover. and then the 3 sections. So hopefully it won't be as intense on future lecture nights, but we will, like I said, on average cover 3 sections a night to make sure we're able to get through all of the course material by the end of the semester. So do you guys have any questions before we call it a night?
Are we allowed to use our notes on the tests and exams?
You will not be able to use notes on the exams, but I give you an exam review. And so you're able to practice and practice and practice till you don't, so it becomes like muscle memory for some of these problems.
Okay, thank you.
Uh-huh. All right, any other questions? All right, if there are no questions, that is all of the material I have for you guys tonight. So you'll have, in my math lab, you'll have homeworks 1.1, 1.2, 1.3. Those will all be due next Monday night at 11:59 p.m. Okay? And then if you guys don't have any questions, I will see you all back here 1 week from tonight at 7 p.m.